All right, so in today's workshop, we're going to take a closer look at crystal field theory, and we're going to look at our d electron counts, reviewing our orbitals, and just figuring out where we put electrons when we have our valence d orbital electrons, where exactly they'll go in our electron orbitals, right? So as a quick review, we can get our d electron count by looking at the group number of our metal. So we'll look at the group number of the metal, and then we'll subtract the oxidation state of our metal. And this tells us exactly how many electrons to include in our crystal field splitting diagram. So this equals the number of electrons in crystal field diagram, right? And as a general review, we need to review our d orbital. So we have 5 d orbitals. We know that we can have our d squared orbital, and that's just going to be, that will look like a kind of a dumbbell with a lobe in the center. We can also have our d x squared minus y squared orbital, and that means that our d orbital will lie on the x and y axis of a Cartesian coordinate. So we'll have our d orbital, I want to make it a little bit prettier, occurring on our x and y axes. We can also get dxy, dyz, and then dxe as our orbitals. And now we want these orbitals to be in between the axes listed. So if we're talking about our dxy orbital, that means that we want our d orbital in the lobes located in between those planes. So we want our lobes in between our x and y axes. I can draw a straight line, it would be great. Our x and y axes. And we'll draw these orbitals occurring in between those planes, right? And then for our dyz, we want dyz orbital. We want our orbital to occur between our y and z axes. So that would actually go here and here, as well as here and here. And then for our dxe orbital, we'll take our z orbital and our x orbital. And now we want our, I'll use a different color, we want our orbitals to kind of go in between those planes. So we'll want our orbitals to go here and here, and then here and here. I think that's kind of the best way that I can draw the orbital diagrams there. So those would be how we draw our d orbitals. Hopefully that was just a quick review. Now what we want to think about is the fact that if we think about our d orbitals, we can start off with our d orbitals being all having the same energy, right? So if they all have the same energy, we have 1, 2, 3, 4, 5 d orbitals. We'll just indicate them as lines now. So we have 5 d orbitals. They all have the same energy, so we'll call this any orbitals that have the same energy degenerate. Right, so they have degenerate energy levels, and we're saying that if there is nothing impacting our d orbitals, right? No ligands impacting the d orbitals of our transition metals, that is what we would expect our d orbital energy level to look like. However, when we do have ligands present surrounding a metal center, we're actually going to get a change in those energy levels. So one shifting that we'll see is for octahedral complexes, right, where we have a metal center. And for our metal center, we have 2 ligands in the axial position, and then we have 4 more ligands in our equatorial position. And this will be our octahedral splitting. And as we have better overlap with our d orbitals, we'll have higher energy, right? And if we just use our Cartesian coordinate system, you can imagine that our dxz and our dx squared minus y squared orbitals will have better overlap with the ligands occurring on these planes. So they'll be higher in energy. And then our lower energy orbitals will be our dx squared, dxz, and dyz orbitals, right? So that's our octahedral splitting. For our tetrahedral splitting, if we look at a tetrahedral molecule, now we have a metal center, and we have 4 ligands attached, right? So this is our tetrahedral shape. And now for the splitting, it actually gets inverted from our octahedral splitting. So now we have 2 lower energy levels that are degenerate and 3 higher energy levels that have the same energy or are degenerate. So that's our tetrahedral complex. And then for our square planar complex, we can kind of consider it to be our metal center. right? And now we've removed both axial positions. So now we only have ligands in the equatorial plane of our metal. So that would be our square planar species. And you can imagine that the best overlap will be our dx squared minus y squared orbital. And then another orbital that has x or y components will have good overlap. And then after that, lower in energy, we'll have our dz squared orbital that has the little lobe in the center here. And then the lowest in energy will be the orbitals with the worst overlap that have a z component, right? So our orbitals that have a z component will be degenerate and they'll have the lowest energy, and they'll be paired together, right? So you also see some numbers there. It kind of gives you an indication of what that splitting looks like. We're kind of thinking of these as being to scale. So we're saying that our octahedral splitting is a certain value depending on the metal, right? The energy difference between these two orbital levels depends on our metal center. And then depending on the shape of our molecule, this energy difference changes, right? So the tetrahedral splitting is 0.4 of our octahedral splitting. That means that they're closer together. And then our square planar is even larger when we look at the energy difference between the highest and lower energy levels when we compare it to our octahedral value. And that delta O depends on the metal. Okay, so hopefully that was a quick review of just how we look at our d orbitals splitting in energy based on the location and identity of the ligands present, right? So for octahedral, tetrahedral, and square planar complexes, for the most part, you'll have to be told which splitting pattern you need. With crystal field splitting diagram is necessary for the metal that you have. Obviously, the number of ligands can give you a big indication of the splitting pattern necessary. So if we have 6 ligands, then we know that we need to use our octahedral splitting pattern because it will be an octahedral complex. However, when we have 4 ligands, that's when we have to figure out if it's going to be tetrahedral or square planar, because both of those have, if you think about our coordination number, the coordination number for an octahedral complex is 6, and the coordination number for both our tetrahedral complex and our square planar complex is 4. So for that, we need to get an idea of exactly what the shape of the complex is. So that's one aspect of how we determine where our d orbitals, where they lie in terms of their energy, the shape of our molecule. The next thing that we want to think about is the identity of the ligands attached to our metal center. So we have 2 options here. We could either have low spin or high spin electron filling occur. So if we're talking about our electron occurring in low spin, let's start there first. What we're saying is that we'll fill our lower energy levels first, and then we'll move on to filling our higher energy levels. So that's low spin. And then for high spin, what we're saying is that we'll fill all of our energy levels singly first, and then we'll start pairing electrons. So that's the main difference there. So what determines whether we have a low spin or high spin filling of our d orbitals, right? So if we have low spin filling, we'll generally see a large octahedral splitting, a large octahedral energy value. This will occur for our strong field ligands, and we'll talk about what that means. Right, so there are specific ligands that we'll consider or name as strong field. For our low spin, we'll also have the minimum number of unpaired electrons. And then also, generally for our low spin ligand, it'll be diamagnetic. And if it's diamagnetic, we're just saying that all electrons are paired. And if we have a diamagnetic species, that means it's not attracted to a magnetic field. And then lastly, we can say that our octahedral energy should be greater than the pairing energy, or the splitting should be greater for the pairing energy. Right, so that's our low spin kind of designation for ligands. We can also have a high spin designation for ligands. And for a high spin, we'll have smaller octahedral splitting energies. These will be our weak field ligands for our high spin. And then we have the maximum number of unpaired electrons. We'll also see that it's generally going to be paramagnetic. And this just means that we have unpaired electrons. And then lastly, our field splitting should be less than pairing energy. Right, so those are kind of the qualities of low spin versus high spin electron filling for our d orbitals for transition metals. And the way that we'll determine if something is low spin or high spin is based on the ligand field. And we're just saying, what impact does the ligand have on the metal center? So if it has a strong impact, it'll be considered to be strong field. If it has a weaker impact, we'll consider it to be weak field. And this will be rank ligands, the known ligands, common ligands, based on something called a spectrochemical series. So if we want to think about the spectrochemical series and ranking our ligands, right? This is a ranking that generally you're given in an exam or you should have access to. Most professors don't make you memorize it, but if we were to just rank them, we see that CO, CN. So now I'm just listing my ligands, or actually I want to put these three in order as well. So for CO, NO, and CN minus, right? Those will be our strongest strong field ligands. And then we have NO2 minus, we have enamine, we have pyridine, which I'll abbreviate as PY, and ammonia, NH3. And then we have EDTA, so these are some of our polydentate ligands. And then we have NCS, our thiocyanate bridge through our sulfur. And then water, our aqua species, our nitrito species, ONO minus. Then we have our oxalato species, our bidentate ligand, our hydroxy group. Then we have fluorine, our thiocyanate S, so SCN minus, actually changes. So the bridging, or the, bonding between either nitrogen or sulfur for our thiocyanate ligand actually determines or changes whether it's going to be strong field or weak field. And then we'll have our halides. So we have the rest of our halides, chlorine, bromine, and iodine. Right, so this is what the spectrochemical series generally looks like. We'll get a specific one in lecture. That's the one that you want. There may be fewer or more ligands included. The main thing to remember, though, is that if we have a strong field ligand, what we're saying is that we'll have a large octahedral splitting, or a large difference in the energy here. And because the energy difference is large, because this gap is getting bigger, what we're saying now is that we'll get a low spin of electron filling. That means that because that energy gap is so large here, we'll fill the lower energy electrons, pair those up before we start filling our higher energy electrons. So that's when we have a strong field ligand. For our weak field ligand, now we have a smaller octahedral split, which allows us to fill our higher level d orbitals singly before we start pairing our electrons. So this will be high spin. And now if we want to think about two examples, we can look at the first example where we have potassium and then iron with our cyanide ligand, right? So we can ignore our counter ion potassium. What we really want to focus on is our metal, which is iron, and the ligand present, CN minus. So we can see that CN should be one of our strong field ligands and low spin, right? So it'll be strong field. The ligand tells us that it's strong field, low spin. The number of ligands that we have gives us the shape. So since we have 6 cyanide ligands, we know that we should also have octahedral splitting. And then the last thing we want to figure out is how many electrons we have to fill in our octahedral splitting pattern. And we can do that by looking at the charge of our metal, right? Because we're filling these valence electrons in our d orbital from the identity of our metal and the charge of it. So since each cyanide ligand has a charge of -1, and we have 6 of them, and the overall charge of our complex needs to be -3, that tells us that iron, Fe, needs to be 3+. And when we do our electron filling for iron 3+, we'll get argon, and we'll lose both electrons in our s orbital, and then we'll have 5 electrons in our d orbital. So it'll be argon 3d5 for iron 3+. And now we can use the fact that we know that we have 5 electrons in our d orbital to actually fill the orbital splitting for octahedral. So now let's look at Let's look at the octahedral splitting pattern here. The octahedral splitting pattern that we see here. And now we want to fill it with electrons. So we need 5 electrons. And since it's low spin, we want to fill the lower energy orbitals first. So now we'll take our 5 electrons and we'll fill 1, 2, 3. And then because it's low spin, we want to pair those energies first, pair those orbitals first, electrons first. So 1, 2, 3, 4, and then we need 1 more, so it'll be 5, right? So that's how the electron filling for K3FeCN, that's what that would look like. Now let's think about the electron filling for our next molecule, where we have manganese with water, and our counter ion is chlorine, so we can ignore the counter ion once again. If we think about the splitting, we still have 6 ligands present, right? This time they're water and they're neutral. If we look at our spectrochemical series, we can see that water is kind of towards the high spin side of our splitting. So now we can draw the orbital splitting for an octahedral complex. So we have three energy levels that are lower, 2 that are higher. And now we need to figure out how many d electrons we have for manganese. And the way we'll do that the same way by looking at the charge of our ligand. So water's neutral, so each water provides a charge of 0. Our counter ion chlorine has a charge of -1, and we have 3 of them, so the overall charge there should be -3. So the charge of our transition metal complex should be +3. Since our ligands don't provide any contribution to the charge, then that must mean that we have manganese 3+. And when we look at our d electron count, we'll look at the location of manganese on our periodic table. And if we go to our periodic table, manganese should be in group 1, 2, 3, 4, 5, 6, 7. So if we just had Mn as the uncharged species, the electron configuration there would be argon, and then we have 2 electrons in our s orbital, and then we should have 5 electrons in our d orbital because it's in group 7, right? And if we want to change the charge to +3, we need to lose 2 electrons from our s orbital first, and then 1 more from our d orbital, so it'll be 3d4. Now we want to take these 4 d electrons, and we want to fill them in our octahedral field, our octahedral splitting of our d orbitals, and we want to make it high spin. So we'll make it high spin, right? We'll make it high spin by filling our electrons singly in our lower energy levels, and then we'll start filling electrons in the higher energy level before we pair electrons, right? So instead of having 1, 2, 3, 4 electrons all in the lower energy level, with our high spin splitting, we'll have 3 electrons in the lower energy level, and then we can promote an electron to the higher energy level, and that's because the splitting here in this octahedral complex, the splitting that we observe between these 2 orbital sets is much smaller. So it's easier for the electron to get promoted to the higher energy levels there.